Okay, hello, good morning, and welcome everyone. My name is Chris Kelson, and I am very proud and excited to be able to offer ATL's first PI presentation in webinar format this morning. And today we'll be talking about concrete petrography, which is something I do and obviously a service that we offer. I know everybody has a full load of work ahead of them today, so we will be very diligent about keeping this presentation to its allotted time frame. So let's start this webinar by giving the official definition of what concrete is according to ASTM. Composite material, right, consisting of a binding medium, the cement or paste, within which are embedded particles or fragments of aggregate. We all know what this is. We've seen it a million times. You have a mental image that probably looks something like this picture, where the binding medium is also the cement or the paste, the gray amorphous fine grain material in between the aggregates, coarse aggregates, fine aggregates, etc. By the way, throughout the course of the presentation, I'll be using my mouse cursor to point things out. So please be aware that that's happening, because I can't use a laser pointer. It's important to realize that concrete is the single most widely used material in the world, and on an annual basis, the equivalent of over 900 Panama Canals worth of concrete is placed worldwide. That's over 5 billion cubic yards of concrete worldwide. So it's a big deal. To offer a brief history of concrete, and by the way, concrete is a Latin word, is derived from the Latin word concretus, which means to grow together. To start with the history of concrete, we need to go back about 12 million years to October 14th, to be exact, when Mother Nature ignited an outcrop of oil shale next to an outcrop of limestone, and the subsequent fusion of those two materials produced a very rough, natural concrete-like mixture. Progressing through time toward present day, starting at around 6500 BC, and again going through almost 400 or 500 AD, humans not only discovered hydraulic cement and started to use it, but started to use it for more and more complex projects and things. Mid-1700s, hydraulic lime began to be used with aggregates. 1824, Portland cement was patented. 1850s or so, reinforcement was used in concrete, and by the 1930s, the first really large-scale concrete structures were being constructed, dams in particular. So we've defined concrete, and I've given you a brief history of what concrete is and has been. Let's switch gears and discuss the other part of this conversation, which is petrography. Let's define that. Petrography is literally defined as a branch of geology. It is the branch of geology that describes and classifies rocks and minerals based on microscopic examination of something we call a thin section. And I'll explain what a thin section is momentarily. The reason why we are interested in marrying concrete and petrography together, because in order for us to learn what we need to know about the concrete, we need to do it at a level more so than our eyes can give. So to explain a little bit further, let's take a look at this random concrete core. Just looking at this, your eyeball will automatically pick out the coarse aggregates, maybe the fine aggregates. Your eyeball can also pick out all of the fine-grained, featureless, seemingly featureless paste in between the aggregate particles. It's easy for your eyes to see small air voids or large air voids, gaps within the paste and between the aggregates. And in this case, your eye can easily pick out an embedded item such as this strand of rebar. But your eyes are only good on that level, but we need to see a little bit more deeply with more details into the concrete. in order for us to do our work here. So to that end, we can utilize several different types of microscopes. I'll explain two different types of microscopes in this presentation. The one on the left is the binocular microscope, also called the stereoscope, and the one on the right is the polarizing light microscope. ATL owns both of these, and they're both indispensable in my work doing petrographic analysis of concrete. The binocular microscope, or the stereoscope, is something that you're probably already familiar with if you think back to your high school science lab day when you were dissecting frog legs or crickets or worms or something. This is what you would use. No sample preparation is required. Whatever you choose to put on the stage underneath the light source is what you're going to see through the oculars. However, the more you can prepare your sample or polish it or clean it, the more detail you're going to see. To give you an example of that, in the upper right of this slide, I'm showing you a concrete core that I've cut in half, but I've also polished it. And if we were to look at that particular portion of the core as outlined by that white box, that's the blow up on the bottom right of the screen, we can see more details than our eyeballs would have normally let us see without the microscope. Details within the paste, again, a lot of the air voids, and even details within the aggregates themselves. The binocular microscope can magnify objects up to about 56 times, so it's definitely valuable, but we need to see even more when we do our petrographic analysis. So to do that, we utilize the polarizing light microscope. That's this guy. This is the bigger, badder, and more expensive version of the stereoscope you just saw. The polarizing light microscope requires the use of thin sections, and a thin section is essentially a glass microscope slide with a thin slice of sample, in this case concrete, that's glued to the top of the slide. And our thin section is then placed on top of the stage and analyzed that way. Also, just as an aside, on both of these microscopes, you'll notice on the top, I've mounted a digital camera so I can take pictures of whatever it is we're seeing through the oculars, and I'll be showing you several of those pictures in this presentation. Anyway, so thin sections are what you need to do, what you need to use for this microscope. So there's quite a bit of sample prep necessary in order to get to that point. Thin section, the upper right is a picture of the original first ever made thin section. The big blue one is what thin sections can look like these days. In real life, the blue thin section is about 3 inches long by 2 inches wide. What's happening here is our slice of concrete, our sample, is sliced so thinly that it will allow light to pass through it. In the case of concrete petrography, we typically make our sample between 25 and 30 microns thick. So a micron is a millionth of a meter, and so 30 microns thick is about 1/3 the thickness of a human hair. That's how thin that piece of concrete is that's glued to the top of the microscope slide. Now, during the process, we can also impregnate our concrete sample with epoxy, and we do that for two reasons. One, the epoxy will hold the concrete together during the cutting and polishing process while we're making our thin sections. Also, the epoxy can be spiked with a color to make the open spaces, air voids, cracks, whatever, in the sample stand out visually to our eyeballs as well as through the microscope. In this case, the epoxy is stained with blue color. So again, this thin section is placed on the stage of the microscope. The light source is down here in the base. The light source is emitted from the base up through the sample, but in between the sample and the light source, the light passes through one polarizer. So as the light goes through the sample, the light is basically filtered into one vibration direction, and we call that plane polarized light, P-L-A-N-E, plane polarized light. As the light goes through our sample, it can go through a secondary polarizer, which we can either insert or remove into the light beam. If we insert the upper polarizer into the light beam, it's oriented at 90 degrees to the lower polarizer. If we're seeing our sample as light's passing through both polarizers, we call that cross polarized light. What that looks like in the real world is this. These two images are taken of the exact same sample that I'm looking at through the polarizing light microscope. The view on the left is what a sample looks like in plane polarized light, and when we look at it under cross polarized light, we see the view on the right. In plane polarized light, you'll notice that there aren't any colors. Everything is almost kind of washed out, just variations of white, maybe gray, and also some little black or opaque minerals. Not all minerals allow light to pass through them. Those are called the opaques, but everything else is a mineral that allows light to pass through. Can't really tell much about this sample through plane polarized light, but when you cross the polars and get this view on the right, now that does something for me as a petrographer. I can recognize what I'm seeing here. What's happening here is that under cross polarized light, the ray of light crossing through the sample is broken up into two beams, and as those two beams of light pass through each mineral, each mineral interacts with those light beams differently, therefore yielding different colors in a very rough sense. That's how it works. And so as I look at this view on the right, I can now see, oh yeah, I'm looking at little rounded, sub-rounded grains made out of quartz. All of these are made out of quartz, and so if you showed me this picture and I knew nothing about it, I would say that's a quartz siltstone or a quartz sandstone or something. The power of the polarizing light microscope is that it can magnify things up to 400 times. So a lot of detail can be brought up using this particular tool. So throughout the presentation, I'll show you different pictures. I'll show you different pictures in those two views. A brief history of the marriage of concrete and petrography. Well, first of all, back in the 1850s is when the polarizing light microscope was first invented. And it wasn't until 1915 when people started to apply the petrographic microscope to study hardened concrete. So the science of concrete petrography is literally, just almost 100 years old, a little bit over 100 years old. So it's fairly young. It's a fairly young science. In the mid 1940s, epoxies were developed to aid in the preparation of thin sections, and by 1960s, we were able to make thin sections that were 20 or 30 microns thick, which enabled us to now do the work that we have. So again, this is a very young science overall. All right. With that being said, here's time for question number one.
Go ahead and click on your response, please. Okay, go ahead, Chris.
Okay. So the punchline of today's discussion is to basically understand what petrographic analysis of concrete can do for us. And I'll walk through a couple reasons in short order, but basically we're trying to learn more about the concrete, or in particular, maybe what's wrong with the concrete. Why is it failing? Now, if your concrete has issues or is failing because of this particular problem, we're obviously not needing concrete petrography to determine why there's a problem in that particular instance. But if you are if you've placed a concrete sidewalk out in front of your building or your house or in your city, and you notice that the surface of the concrete is starting to deteriorate, why is that happening? Well, that's where petrographic analysis can help. If you have a retaining wall or a dam, or again another sidewalk that's showing cracks or efflorescence or pop-outs, why is that happening, right? Those aren't normal things that should be normally happening to concrete. Again, petrographic analysis can help determine what the cause or causes are for the problems. If your stairs look like this, clearly that's not what should be happening. We can help with the petrographic analysis. Another sidewalk. If you've ever walked on a sidewalk and it makes a hollow sound as you walk on it, and large portions are just flaking off the top, why is that happening? Again, I can help with petrographic analysis. Also, we can use petrographic analysis to do more forensic type work. For example, we have a placement of concrete that may have been affected by fire. There was definitely a fire there. Was the concrete affected? Petrographic analysis can help determine if the concrete was compromised. And just as a quick aside, concrete problems and issues with concrete deteriorating come up fairly regularly, more than you'd think. I happen to run across this on the People's Court, where this lady actually brought in her contractor because her driveway was failing. There are the pictures, and she blamed it on the contractor doing shoddy work. The judge saw the pictures and basically awarded her $2 grand for the shoddy work. My question is, why didn't the contractor do a petrographic analysis of that failing concrete? He may have been able to show that the ingredients that made up the concrete were not compatible with each other, or something was wrong with that, and it wasn't a contractor issue. It may have been something with the concrete itself. Anyway, he didn't do that. She won. Just a mental note. All right, so petrographic analysis of concrete can determine a lot of things about the concrete, and here's a list of them, a partial list, and we'll talk about some of them in today's presentation. Using petrographic analysis to determine why it's failing is probably the most common reason why I do this work. But you can also determine some very basic aspects of the concrete: water cement ratio, aggregate types, the air, what type of air and how much in the concrete, is it carbonated, so on and so forth. Anyway, what I want to do is walk through some of these issues listed here and discuss them in turn. Let's start with why concrete fails, and the first failure mechanism we can discuss are these chemical reactions that occur between the aggregates and the paste in the concrete. These are collectively referred to as AAR, or alkali aggregate reactions. Essentially, what we're referring to here is the fact that the aggregates in the concrete and the cement or paste in the concrete aren't playing well together chemically, and the resulting disequilibrium results in concrete failure at some point. So just a couple of broad points. First of all, as far as the aggregates are concerned, depending on what type of aggregate is being used in the concrete, its elemental constituents will be different. But suffice it to say, no matter what your aggregate type is, what type of rock it is, it will have SiO2, right, referred to as silica or quartz. It'll have carbonate, CO3, and some aluminum oxide. Those are just basic building blocks in essentially every rock and mineral on the planet. As far as the paste is concerned, just keep in mind that the paste is very alkali-rich. Okay, it's very rich in potassium and sodium, and water in equilibrium with that paste is really basic in pH. It's like a 13 or 14 pH. So as far as the aggregate paste reactions are concerned, let's discuss two in particular. One is ASR and one is ACR. Let's talk about ASR first. ASR stands for alkali-silica reaction. And again, this is a reaction that's occurring between the alkali in the paste, water, and aggregates that contain certain varieties of silica-rich minerals. So here in blue, I've listed the silica-rich minerals. What they all have in common, SiO2. Right, I mean, essentially everything here. Opal, chalcedony, cristobalite, and tridymite, those are polymorphs of the mineral quartz. Volcanic glass, right? Obsidian, any volcanic rock, chert or flint, if you like that word better, and strained quartz as well. Strained quartz, I'll show you a picture of that a little bit later on. Just remember that term, strained quartz. But those guys are notorious for contributing to ASR. What happens is that the alkali in the paste and water and silica from any one of these minerals produces a gel which expands with water. The expansion then causes the concrete to fail. ASR was first identified by Tom Stanton back in the 1930s in California, just FYI. So for those of you who need your morning dose of chemistry, here is the equation that explains how ASR gel is formed. Here is our quartz, our silica, water that's just in the paste, alkali in the paste, and that water, by the way, can be, I mean, it's moisture moving through the concrete after it's hardened. Those three things combined to give you our gel, our ASR gel. Now notice the gel is hygroscopic. It has water in its formula, and it's amorphous. This isn't a mineral. It doesn't have any crystal structure to it. It's a gel that expands when it gets wet. Macroscopically, this is what ASR looks like. Map cracking, pop-outs, maybe reaction rims around aggregates, if you can see the inside of concrete that's afflicted with this stuff, or efflorescence, which is usually this white colored stuff, for lack of a better word, that you see coming out of the cracks of the concrete. Map cracking is attributed to ASR. Cracking in concrete can be caused by other things, but ASR definitely does it. Here's another example of what ASR looks like on a little bit closer level. There's a piece of core that I've cut in half and I've polished. I've also brushed a pink powder over the surface to fill in all the open spaces and cracks, just to show you how pervasive the cracks are through this material. The cracks go through the paste, they go through the aggregates, paste aggregates. They don't go around the aggregates, they go through everything. So this is a good example of material that's being afflicted by ASR. Under the microscope, this is what I see when I see ASR. We're looking at this in plain polarized light. So all of the pink that you see that's the epoxy showing you open spaces within the sample. The big blocky objects are aggregates. The fine-grained brown-colored stuff in between is the paste, and the gel is this material here within the paste. It almost has layers to it. It's cracked. So that's the ASR gel that's causing this sample to crack. Here's another picture. Now we're looking at this sample under crossed polarized light, so a little bit different view. Again, aggregates, aggregate, aggregate, aggregate. All of the fine-grained material, that's the paste. This large object in the lower center is an air void that is partially filled with ASR gel. This is the gel, and you can see this is the gel, and you can see it cracks. So when it desiccates, when it dries out, it cracks, it loses volume. When it gets wet, it expands. And the gel is mobile. Okay, so it forms within the concrete, and then it migrates through cracks or into air voids or whatever. So wherever you see the gel isn't necessarily where it formed. I mean, it's generated at the aggregate, in the aggregates in the paste, but it can migrate once it's formed. Here's another example of this is an air void within the paste that's filled with ASR. That whole thing is just filled up with ASR. This is in plain polarized light. Notice this one has a little bit, this one has none, this one is completely full. So just another view. And another picture of ASR gel within the sample. This one's a little bit more interesting, I think. This is in plain polarized light again, so pink is open space. The red dashed line indicates the boundary of an air void. So when this concrete was born, this whole thing was just complete empty space. Here's your paste, and here are your aggregates. Anyway, over time, water that was migrating through the paste started to leach out or pick out certain ingredients from the paste and redeposit those elements as the mineral etrangite inside this void. Etrangite so this is a secondary sulfate mineral. It's not bad or good. It's just there. But this is showing that water has been moving through the concrete. However, notice on top of the etrangite you have ASR gel. So if I was looking at this sample for a client, I would be able to tell them a little bit about the history of the sample. The sample had pre-existing air voids. The sample has experienced water migrating through it. The water leached out certain minerals and precipitated it as etrangite, and then at a later date, ASR gel, which formed within the sample, was deposited on top of the etrangite. So I know the gel is younger than the etrangite. You know, whether the gel formed last Tuesday or 6 years ago, I don't know, but I can relatively tell, you know, what formed before what. And that's part of what we pass on to the client. So as I mentioned before, you need 3 ingredients to form ASR gel, and you know, you need the silica, you need the water, and you need the alkali in the paste. And once those 3 things mix together and ASR starts, you're not stopping it. The only way you can completely keep ASR from forming in the first place is to remove one of those three contributors, but that's not very viable. So what can you do about ASR? I'm not going to go through this entire slide here, but I can say that you can try to mitigate the formation of ASR first and foremost by paying attention to the type of aggregates that you're using in your paste. If your aggregates contain, you know, chert or cristobalite or strained quartz, that's probably not a good aggregate to use unless you are able to use, you know, low alkali cement. If you're able to add pozzolanic mixtures, admixtures, slag, pumice fly ash, silica fume into your concrete to kind of offset that trifecta of chemistry that makes ASR. So there are some ways to try to mitigate the problem. You know, I've seen concrete that's 100 years old that has no ASR, and I've seen concrete that's 3 years old that has it. So yeah. Anyway, that's about the best you can do. All right, time for question number 2.
And enter your responses now. Go ahead, Chris.
Okay. The second type of alkali aggregate reaction is called ACR, stands for alkali carbonate reaction. Here we have the same basic story where we have chemical disequilibrium happening between the aggregates, the alkali in the paste, and water. However, in this case, the aggregates aren't silica-rich, but they're dolomite-rich. They're either dolomite or dolomitic. Dolomite is like limestone, only it's got magnesium to it, in it. So that's the difference. And petrographically, I can identify dolomite. But it's a chemistry thing too with the magnesium as well that separates it from limestone. So the dolomite in the concrete, once it mixes with or interacts with the alkali in the paste, it gives you these byproducts or these products. The dolomite turns to calcite. You get sodium carbonate and then a mineral called brucite, a magnesium hydroxide. Now the conversion of dolomite to calcite is something called de-dolomitization. And the initial thought was that as you're converting dolomite to calcite, you're creating byproducts that again expand and crack the concrete. I mean, the problem with ACR is that you get cracked concrete just like ASR. The only problem with this is that the products take up volumetrically, they take up less space than the reactants. So this stuff doesn't really, these three things don't necessarily explain why the concrete cracks when ACR is at play. ACR is poorly understood. It's been documented in the literature for the past 50 or 60 years, but it's very poorly understood even today. It has a close association with ASR. They're often found together, and the current thought is that this ACR is a function of these dolomite aggregates not being completely pure. In other words, that we're dealing with dolomite aggregates that have impurities in them, and those impurities would be clay minerals or that may expand with water, but also silica, little quartz inside with the dolomite aggregate. So this picture is a microscopic image of what a dolomite aggregate looks like. All of the gray and white and black chunks that you see in that aggregate particle are quartz. All of the brightly colored specks that you see in there, for lack of a better term, those that's dolomite, calcite. But even in between those little particles, at magnifications that would require more than what I can show you here, there are the little clay minerals that may be contributing to the disequilibrium. So the quartz and the clay within this, and this is nothing that we can we can't do anything about this. This is how Mother Nature made that rock. That's just how it is. And again, we just have to be careful using this aggregate type to try to get away from the possibility of ACR. All right, let's switch gears briefly here and talk about another facet of the concrete we can identify and work with petrographic analysis, and that's to determine if the concrete is carbonated or not. So carbonation of the concrete results from the formation of carbonic acid, H2CO3, and that's from water and CO2 that's in the atmosphere, it's in the soil, it's everywhere. So concrete that's even indoors will carbonate, not just exterior concrete. But the carbonic acid, once it's formed, interacts with the portlandite, the calcium hydroxide in the paste, to form calcite in water. So here we're forming calcite again. We're forming calcite in the paste. We're turning the portlandite into calcite. That's the carbonation we're talking about. And the rate at which carbonation occurs depends on a lot of factors. It depends on temperature and humidity, interior versus exterior concrete, the water cement ratio of the concrete, everything. So it's impossible to say how fast carbonation will grow or extend into the concrete from the surface that's exposed to the atmosphere. Generally speaking, the older the concrete, the deeper the carbonation horizon will be. The effect of carbonation is that it lowers the concrete, it lowers the pH of the concrete paste from 13 or 14 to less than 9, and that reduces the permeability of the paste, which means it's less susceptible to chemicals, externally applied chemicals getting in and ruining the concrete. The problem, though, is that when you carbonate the paste, if that carbonation front extends down to where there are embedded steel items, the lowered pH of the paste removes the protective passivity layer that's surrounding the steel, and therefore the steel will start to oxidize, it will rust and corrode, and that itself will expand, cause byproducts that expand and crack the concrete. So carbonation it's a double-edged sword. It's both good and bad. In hand sample, you can visually kind of determine where carbonation starts and stops. This is a core taken from a sidewalk. So this end of the core was the sidewalk surface. And by applying a phenolphthalein solution, you can see where the boundary is between carbonated paste and non-carbonated paste. So the phenolphthalein basically points out the paste with a pH lower than 9, and anything above 9 will be stained purple. So there's your carbonation horizon right there. Notice it's not flat. Notice it's not uniform. It undulates through the sample, but from the surface down to here, that paste is all carbonated. And if we have a sample of concrete that's exposed to the on 3 sides, in this case, to the atmosphere. This was from the top of a retaining wall. So left side, top, and right side were all exposed to the atmosphere. Carbonation was starting to work on the concrete from all 3 of those sides inward. So just the center is not carbonated, but all 3 outer edges are. What carbonation looks like under the microscope is shown here. This is a sample from again a sidewalk. Notice the scale bar, 500 microns, right? So this is a sidewalk surface, and we're looking at this under crossed polarized light. I've added this white dashed line to show the boundary between carbonated paste and non-carbonated paste. So that's easy for me to see. And I can measure the distance from the surface downward down to a micron and tell the client how deep the carbonation is. But I want you to notice that the carbonation horizon extends really, really deep in this part of the sample. And so, you know, I look at that and I'm trying to figure out why that is. So let's take a look at this yellow boxed area under a little bit higher magnification. I'm now looking at that same view under plain polarized light, and what I can see, so here's our epoxy that's colored in blue, right? In cross polarized light, that epoxy is black. Anyway, so here's our epoxy, and notice that you can see a crack. It's like a bleed water crack or something that goes from the surface down, 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 then down, 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 all the way, all the way, all the way. And that bleed water crack essentially acted as a pathway. It's like a little highway where all the water and oxygen got in from the atmosphere and carbonated the paste around it. Therefore, there's the crack, and it extended all the way down here. Therefore, the paste carbonated on all sides of that crack. That's why it was deeper there. So I'll point that out as well. I just threw this picture in because I thought it was kind of cool. Carbonation can occur in a little bit in a similar way, but in kind of in a different format. This is a small limestone aggregate. Limestone is made out of carbonate, it's calcium carbonate, but water in the cement paste has been interacting with this limestone aggregate, and the limestone aggregate has been basically bleeding carbonation out into the surrounding paste. So even though the carbonation front isn't anywhere near here, the paste immediately around this little aggregate is being carbonated from that particle. All right, question 3.
Go ahead and answer your responses now. Go ahead, Chris.
Okay. One of the most common questions that clients have when they give us samples for analysis is why is the surface of the concrete failing? You know, why isn't it behaving like it should? So I'll show you a couple of pictures of what we see. This is a photo montage of the surface of a sidewalk, of a core from a sidewalk sample. This is the surface of the sidewalk, and just looking at this photo montage, I just want you to be able to see a couple things. First of all, large, big aggregate, smaller aggregate, a lot of aggregates. Okay, paste, black or gray in between the aggregate particles. The epoxy is blue, so air voids and cracks are blue. What I want you to notice is the difference between the paste that's at the surface of the sidewalk and the paste down deeper. And in fact, we can draw a line basically separating this paste from this paste. And if you look closely, I hope you can see that all the paste above that yellow dashed line is A, lighter in color, and B, contains a lot more open spaces and air voids than the paste down below. And if we took a look at this more closely, we can see that even more clearly. Here's the surface of the sidewalk where aggregates and paste was being lost, and you've got this very rough surface, right? That's the failure the client noticed. All of the open spaces in the paste here, and not so much down here. So with that, so when I see a sample like this, I would deduce that the uppermost paste had more water in it than the paste down below. The more water in that paste, whether it rained on that cement, whether it rained on the concrete when it was placed and got a bunch of water on the top, whether it was finished incorrectly, whether the contractor blessed it too much and they were trying to finish it. I don't know what did it, but too much water in the uppermost paste made the paste weak and easy to just flake off, and there's no strength to it. And if this sample had gone through a winter, that paste wouldn't have survived a freeze-thaw cycle. It's just too weak. And all of those open spaces that we can see here in the uppermost paste that are now filled with air, when this was placed, those are filled with water. And so clearly it was just, the paste was too water rich. Without being there to see what did that exactly, I can't say, and I won't point fingers. That's what causes the failure, and that's what I pass along to the client. Another aspect of the concrete that we can determine is the water to cement ratio of the paste. So this is the ratio of the weight of the water relative to the weight of the cement. In an ideal world, you'd need 0.35 kilograms of water for every 1 kilogram of cement in order for all of the hydration reactions in the cement to reach completion. In the real world, the water cement ratio is between 0.45 and 0.6. That's typical. I see things a lot higher than that, and not so much lower, but a lot higher than that, especially at paste that fails. Generally speaking, the lower the water cement ratio, the stronger the concrete is going to be. So in instances where the paste was blessed with too much water, it was too water rich. Again, it was just too weak. So there is no magical instrument that we possess that determines the water to cement ratio of paste. This is all done through microscopy and with the microscopes and with my eyeballs. And we can estimate or determine the water to cement ratio to 1 digit, maybe 2. Past that, I think anybody's stretching it, but 2 digits is standard. So to give you an idea of what I do, and here I'm showing you 2 pictures of cement paste through the microscope, but in this case I'm using fluorescent light. I can spike the epoxy with a dye that will fluoresce under fluorescent light, which makes the water cement ratio determination easier. On the left, the black objects are aggregates, and in between is paste that has a water ratio of about 0.35. On the right, the paste has a water to cement ratio of 0.6, about double. So microscopically, it's easy for me to see relative differences between low WC and high WC and estimate them accordingly. So a couple other things. We can determine the porosity of aggregates or rocks or concrete or construction materials, right? The percent of open space, which in the sample, which of course all those four aggregate durability and strength are certainly key to that. This is a sample of a CMU, cinder block, right? That's cut and polished. On the left, on the right is a close-up. Again, I put some of that pink glitter in there to show you open spaces with your you can see with your eyeball. Under the microscope, again, making a thin section of this material, we can see the pink spaces in between the paste. They're the aggregates, and the aggregates themselves have porosity to them. So we have, you know, my microscopes here have the ability to calculate what the percentage of open space is, either in an aggregate particle or in that entire field of view. And that's, again, data that we can report to the client. I mentioned earlier also that we can use petrographic analysis to determine if concrete was affected by fire. Again, concrete placement here, a wall. There was a fire on the wooden forms above it. This is this hole here was made by extracting this core. So the sample, the surface that was exposed to the heat is the top here, this top flat part. Cut and polished sample we're looking at. Notice that your eyeball can't really pick out any discoloration, any apparent damage in that surface. Looks okay. Under the microscope though, again, there's a scale bar, 200 microns. This is the same surface of the sample. Notice under fluorescent light, we can see that the paste and the aggregates are cracked, and there's discoloration in the paste. So my petrographic analysis showed A, the paste had been dehydrated right at the surface, and B, thermally expanded or cracked down to a certain depth. And again, that's data that I report to the client, and they can determine course of action from there. All right, question 4.
Should appear momentarily and go ahead and answer. Okay, go ahead, Chris.
Okay, just to wrap up a couple loose ends here. Petrographic analysis of the concrete can yield just basic information of the concrete. Sometimes a client will give us concrete and they don't know what it's made of, they don't know what the aggregates are, and it's just basic petrographic analysis from that point. So if that's the case, I can just tell them basic information, such as, you know, in this particular sample, the aggregates are made out of a limestone, a carbonate rock, probably a limestone. I can see fossils in the rocks, brachiopods, crinoids. If you give me a minute, I could probably determine how old that rock is based on the fossils in there. In the aggregate on the right, there's a vein of calcite, just features to note, and I pass that along. I also know that the fine aggregates are made of a different rock type. Everything in the white circle actually came from an igneous rock, something like a granite maybe. So wherever, you know, whoever made this concrete used aggregates from 2 different rock types at least. I can identify rock types. In this case, the rock type is metamorphic. This is a quartzite, so a quartz siltstone or a sandstone that was metamorphosed. That's that guy. And also notice that the smaller aggregates are, again, a different different rock types. Here we have limestone particles, and over here we have large pieces of quartz, which again probably came from an igneous rock. So whoever made this concrete used aggregates, I think, from 3 different rock types. Petrographic analysis can also identify, you know, we can use it for not just concrete, but also in this case shale. Sometimes clients want to know if they have to worry about building on shale that might expand, and this is what that looks like. Shale under the microscope is pretty boring in my opinion. It's just layers of sediment, right? Very fine-grained sediment. In plain polarized light, I can identify some of the sediment containing carbonate and clay and quartz, but then we see some of this black material in there that I can't really identify. It could be organic matter, or it could be, in this case, pyrite, otherwise known as fool's gold, right? That's an iron sulfide mineral. And the problem with pyrite is that if it exists in your shale, along with carbonate, like calcite, you add water to that, you can get a secondary mineral called gypsum, which would then form. That takes up more space than the initial reactants, and that would cause your shale to expand. So I utilize the microscope to determine that. And one last thing, we talked about strained quartz. You might have heard that term with respect to aggregates and ASR. This is what strained quartz looks like under the microscope. It's a little video clip I'm going to show you that's about 4 seconds long. But basically what we're looking at here, my cursor is pointing out a large quartz crystal. Now, as you rotate this sample underneath the microscope, on the microscope, every 90 degrees, in a perfect world, that quartz crystal should go completely black. It's just like flipping a switch. You'll see color, gray, maybe light yellow, and then it'll go completely black every 90 degrees. If it's strained quartz, the quartz doesn't go black at every 90. It undulates and gently goes into and out of black. So watch the video here. Let's see if we can get it to work. So as I rotate the stage, see how the quartz goes dark on the edges and then fades into the center. Dark on the edges in the center and fades out to the edges. See that? So that tells me that this quartz is strained. In other words, it's strained because Mother Nature applied enough heat and pressure to that quartz to actually bend the atomic structure of that quartz, making it optically do that. But in the course of bending the atomic lattice, Mother Nature has made that particular grain of quartz really susceptible to alkali and water interaction, therefore forming ASR. So identifying strained quartz is a lot of what I do. All right, here's question 5.
Question should appear momentarily. Go ahead and enter your response. Go ahead, Chris.
With that being said, folks, that's the end of the webinar. I appreciate your attention and your willingness to see this morning. I'm game to answer questions or field some comments if anybody has them. Howard?
Yes, we have one question, and it's about the fire sample.
Mm-hmm.
Was the cracking caused by the fire, or could it have cracked previously from something else?
That is a good question. So my opinion with that particular sample was that the heat of the fire affected the outermost surface of that sample and probably caused the cracking. That's what I'm putting money on. The other option would be that the sample was cracked maybe during extraction, right? The depth of the cracking and how it was limited just to the surface made me think more toward the heat doing it, and also the fact that the paste and the paste was also dehydrated as well as cracked, kind of led me to believe that the fire did that. That's my story, and I'm sticking to it. Thank you for the question. Anything else, Howard?
That was the only question.
Okay. I thank you again, everybody, and feel free to contact me if you have any questions about this or if you want to discuss anything further. Thank you very much.